Welcome to the Chalk and Talk Chem 2005. Today we will talk about heteroaromatics and 5-member rings. The most representative of the 5-member rings is down here, is a Pyrrol. Why is aromatic? Because we have 2, 4, 6 electrons. Remember that the pair of electrons of the nitrogen are in the pz orbital, forming part of the aromatic system, of the p aromatic system. That means 6 electrons follow the rule of 4n plus 2, is cyclic, and is planar. That means this is aromatic. What are the properties of Pyrrol? Well, we will always compare any heteroaromatic that we will study with the benzene. Okay, benzene will be our leverage, level 0. Okay. If we analyze the Pyrrol, we have 6 electrons, but we only have 5 atoms. If we do a fast mathematics, each atom has 1.2 electrons. I understand that the nitrogen is more electronegative than not the carbons and will have a slightly more electronic density. But even with this, each of these carbons will have more than 1 electron. That means this ring will be electron rich. And this is the most important, because this will define the chemistry of the Pyrrol. Okay? It's electron rich, and this will define his chemistry. Okay. How we can prove that it's electron rich? Well, if you do an NMR, okay, if we do an NMR of these two, of this compound, we have these 2 hydrogens. If were benzene, if these 2 hydrogens were from benzene, we will get that this will appear in NMR around 7.1, 7.2 ppm. Okay? If this ring is electron rich, what we will expect is that this hydrogen will be more shielded because it's electron rich. That means that it has to go down in ppm. That means that we will expect this to be lower than not 7.2 ppms. And if we do the NMR, exactly, these two are around 6.6, 6.9. 6.2, 6.9, depending on the substituents. Okay? That means the NMR proof that these 2 hydrogens are, that this ring is electron rich. If the Pyrrol is electron rich, what is the consequences chemically? If it's electron rich, means the electrophilic aromatic substitution will work very well. Why? Because it's electron rich. That means this pair of electrons will be able to attack any electrophile. And just the opposite, in the nucleophilic aromatic substitution, will be a bad substrate. That means will work very badly. Okay? This is because the Pyrrol is electron rich. Okay. Then, what we can say about the Pyrrol? Is basic the Pyrrol? Well, we have a pair of electrons in the nitrogen, but what we did at the beginning, we put the pair of electrons in the pz orbital to be part of the p aromatic system. If these pair of electrons are part of the p aromatic system, are not accessible. If we use this pair of electrons, for example, to take a proton, what is happening is now this nitrogen is sp3, hybridized. If it's sp3, we don't have a pz orbital to form the p aromatic system, what means that this compound becomes no aromatic. And we know that this is not stable. It's better to be aromatic. For this reason, Pyrrol is not basic, or is very few basic. Okay, because simply the pair of electrons of the nitrogen are not accessible. This also is important in order to know the reactivity, how we can do a substitution in the nitrogen. We take Pyrrol and we want to do a substitution in the nitrogen. For example, we want to put a methyl. Our first option is this, add methyl iodide, isn't it? The pair of electrons can attack here, SN2, and we get the methylation. But again, the pair of electrons of the nitrogen are not available because are part of the aromatic system. That means that this reaction will never take place. What option we have if this is not possible? Well, if we want to make a substitution in the nitrogen, what we need to do is, in first instance, we need to remove this proton. We need to remove this hydrogen. How we can do it? By the addition of a strong base. For example, butyllithium, or even sodium hydride, a strong base. Terbutylithium, LDA, all the options that you know. What will happen is that basically this will take the hydrogen and we will get the anion of the Pyrrol. And this anion can react with, for example, methyl iodide. Again, this attacks here, SN2, and what we get is the methylation of the nitrogen. Basically, we can do this with any electrophile. Okay? That means important, if we want to make a substitution in the nitrogen, the first step must be always the deprotonation of the Pyrrol. Okay, then we can go to the electrophilic aromatic substitution. Okay, electrophilic aromatic substitution. We can do an exercise of remember in the benzene ring. We have the benzene ring, and the typical reaction is we add nitric acid and sulfuric acid, and what we get is the nitration. Okay, this is a typical electrophilic aromatic substitution in the benzene. What is the difference if we try to do the same with Pyrrol? Well, the first difference is that this is an activated substrate. Why? Because it's electron rich. That means that it will be easier to nitrate the pyrrole than not the benzene. Basically, it will be easier to do any electrophilic aromatic substitution with pyrrole than with the benzene. And what means this? Means basically that we can do the reaction in a softer condition. For example, we don't need to add nitric acid and sulfuric acid. We only need to add, for example, this, and what we get is nitration. Okay? Why I put the substituent in the middle? Because we will talk about the selectivity or the regiochemistry a little bit later. That means any reaction that you do with the benzene in the electrophilic aromatic substitution, you can do exactly the same with the pyrrole, but with softer conditions. Okay? There are examples in the notes of all the reactions that you can do with pyrrole in the electrophilic aromatic substitution with the conditions for the pyrrole. But the trick is that if you don't remember how to do a reaction with pyrrole, that means if you don't remember this compound, this reactant, don't worry. You can use the same reagents that you are using for benzene. You know that will work. Okay, and the paper will work. In real life will be a little bit different because these conditions are very strong, and probably what you will get is the polymerization of the pyrrole. But any condition that you put in the benzene basically will work with pyrrole, and it will work faster. Okay? This is one of the tricks. And now we will enter in the substitution. Of course, when we do an equation in the benzene, what is happening is that all the positions of the benzene are exactly the same. If we don't have any substitution in the benzene, that means all positions are the same. However, in the pyrrole, we have two positions, isn't it? One that is closer to the nitrogen, one that is far away of the nitrogen. That means that will not be the same. Which is the preferred position in the electrophilic aromatic substitution for pyrrole? Well, in order to do what we need to do, we need to analyze the intermediate. Okay? I will do it in a very generic case. We have here the pyrrole, and we react the pyrrole with an electrophile. We know that any aromatic that is reacting with an electrophile, basically the pair of electrons will attack the electrophile. Okay? And we will generate, in this case, for example, if we attack in the second position, we will generate this intermediate. In order to know if this intermediate is stable or not, what we need to do is to draw all the resonance structures. If I put this pair of electrons in this position, I generate this resonance structure. If now a pair of electrons is moving here, I will get okay? And be careful, because this is the most important resonance structure. Why? Because in this resonance structure, despite we have the positive charge in the most electronegative atom, all the atoms are having the octet. And this makes this resonance structure the most important. Okay, we have 1, 2, 3 resonance structures. What happens if instead to the second position, we go to the third position? Okay, it's the same reaction, the only that now the electrophile is added in the third position and we have the positive charge here. Well, we can move it. And we generate this resonance structure. Again, this resonance structure will be the most important because all the atoms has the octet. Now maybe you are tempted to do this. But if you put this double bond here, what is happening is that you are breaking the octet of the nitrogen. That means that this is not possible. You cannot break the octet in the nitrogen or in the carbon. That means this possibility is forbidden. That means that we have two resonance structures. That means here, okay, we will get if we do the attack in C3, we get two resonance structures. If we do the attack in C2, we get three resonance structures. That means this will be more stable. This will be the preferred product. That means the electrophilic aromatic substitution will go to the C2 position in the case of Pyrrol. Okay? This is exactly the same in the case of the other heteroaromatics that have 5-member rings. For example, all these compounds Pyrrol, furan, and thiophene will have the same reactivity. The preferred position for the electrophilic aromatic substitution will be C2. What is the difference between Pyrrol, furan, and thiophene? Basically, the difference is the reactivity. Okay, this will be more reactive. Why? Because it's electron rich. This is also electron rich. You can do the same count of electrons and you will see that it's exactly the same. However, because the oxygen is by far more electronegative than not the nitrogen, this oxygen is attracting more the electrons of the p system, making the rest of the carbons less electron rich. That means that B will be less reactive. And finally we have the thiophene. The thiophene will be the less reactive of all. Why? Because in this case it's not so important the electronegativity, but the thing that affects more the reaction with thiophenes is that the sulfur is from the third period. That means that his orbitals are very big if you compare with oxygen or with nitrogen. Then the overlapping between the sulfur and the carbon is not very good. And this is even worse in P systems. That means that the difference of the size of the orbitals of the sulfur with the carbon make this compound the less reactive of all. Okay? That means in the electrophilic aromatic substitution, this will be the most active, furan will be the second more active, and thiophene will be the one with less reactivity. Okay? But all of them will direct to the C2 position. But what happens if we have other substituents? For example, what happens if we have this compound and we try to do the annihilación? Okay? Or even better, we add an electrophile. Better to put general. What is happening? Okay, we know that the Pyrrol orientates to C2 position. This is the orientation of the Pyrrol. This position will be active. But we have a substituent. How is affecting this substituent? The substituents in the electrophilic aromatic substitution of heteroaromatics will have exactly the same behavior than the behavior in the benzene chemistry, in the electrophilic aromatic substitution of benzene. For example, this methyl is activating the electrophilic aromatic substitution by induction. That means that this will orientate in the benzene ortho para. Okay? Good. Then if it's orientating ortho para, we do exactly the same with the 5-member ring. Here is ortho, this position is ortho, this position is meta, isn't it? That means one far away ortho, two far away meta. And realize that I do this count always going through the carbons. I will never do it over the nitrogen. That means if I try to do this, ortho, meta, para. This is forbidden. This is not working. Never, never we have to count over the nitrogen. Never. Okay, it's ortho, stop. This is the nitrogen. No more. Okay, for the other side, ortho, meta. No more. Okay, that means in the case that we have here, if the methyl is activating the ortho and para position, it means that we will activate these positions, this and this. As, sorry, this has been my cut. As the Pyrrol is orientating C2, we have two orientations in this carbon. That means that this carbon will be double activated. We will have this final component. Okay? What happens if instead of a methyl we have, for example, a nitro? We do exactly the same than before. We add the electrophile, and then we know that